right, so reaction rates, a completely new topic. It's all obviously, as you're seeing as we're going through all these, that they're all related to everything that we've learned and we use that as we go. But kinetics is motion, of course, of reactions, and we're talking about the rates that reactions occur at. So why do we care? I mean, I think we care when we're taking a medication. Say you have a really bad headache and that aspirin or Tylenol you're going to take, I want that to act pretty quickly because I don't want to deal with this headache. But I also want it to maybe have a little bit of slow release, that it's going to take time and stay there so that I can not get another headache. Other times you want medications that are going to release over time so that you can not have to keep going and getting like an injection or whatever it is. Okay. So collision theory is just a theory that says that obviously molecules will collide. And they do, because all over we're looking, we can't see them in the air. They're all banging into each other. And the collision molecule says, though, if something's going to react, we have to have enough energy for that reaction. That energy is called the activation energy. I always think of the Wonder Twins, probably too old of a commercial for you. I wish I could put a little boop in here and just show you the Wonder Twins. But they used to have these two little rings, and they'd say, Wonder Twins, activate. And they would be like a form of a water in some form of machine. It was really quite silly, but that's exactly what happened. They need to have that energy to say, yay, we get to proceed with the reaction, or no, the reaction doesn't occur, and they will bounce off each other unchanged, nothing happening. So it's called the activation energy. The abbreviation we're going to use is energy of activation. So an E, big E with a little a, and that amount we're going to see, as far as what we're going to see do, will change depending on whether the reaction is endothermic, exothermic. All kinds of different things will affect the activation energy. All right. So here we go. So we're going to show you what we have here is an energy profile. So we have, it's called Gibbs free energy. It's just after scientists that called this. It's actually used as a G for Gibbs, as you see here. That really, from what we have learned, is delta H. It's the same thing, okay? So delta H, or the enthalpy of the system, the heat needed for that to happen. We're seeing that it starts at a certain energy here, okay? Now, we don't have numbers on this one. Others we do. And then it just tells us, hey, here's our reactants, here's our products. The reaction is going to proceed. And the reactants, look what happens to the products. They are at a lower energy. And when you're at a lower energy, that means you lost energy. And the delta H will be negative. And you see here, it says delta G is less than 0. So that means it's going to be a negative value. And that means it is losing energy, and that means it is exothermic. All right. A reaction is spontaneous usually when it is like that. It's just going to like fire, boom, okay, it's going to burn. We're not going to do anything about it. It does have to have oxygen and the reactants that it needs, but that's about it. On the other hand, over here, you see, the reactants start way down here. They don't have to start way down. It's just relational. The products end up with more energy than the reactants started with. So that's the only thing that matters. And the difference between where the reactants have energy, now I don't love, they kind of drew that line a little lower than really where the reactants were. They should have drew it a little higher. But anyway, this delta H here, the reactants, right, between the reactants and product energy, between the reactant product energy, this time it is positive because we are gaining energy. And when we gain energy, we are endothermic. So that would have a delta H that is positive. And that reaction is usually not spontaneous, and that is what we are going to look at, or at least talk about. So on the next one, we have a little bit more that we can put on these diagrams. I just wanted to get the basics first. So we look at this right here, and we are going to label the activation energy, the heat of reaction, the delta H, or Gibbs free energy, the same thing. So this is just one thing. I'm going to choose to label it delta H because that's the enthalpy that we're familiar with. The reactants, the products, and label as endothermic, exothermic. So we got a couple things going on. I think since we just talked about it already, we know, we always start with reactants. Now, I'm just going to put an R for reactants instead of writing it out, and a P for products. I let that happen so much, okay? And I don't need you to write it all out as long as we understand, okay? So we already know on either profile. Now I'm just going to do this because it's so stupid, right? Easy, hopefully not stupid easy. Sorry, I didn't mean to say that, but it's a little bit easier, right? Reactants always on what we start with, products always what we end up with. Now, we are going to learn that There is a forward reaction, which means reactants to products, but we can also diagnose this and look at this and tell a lot of things about it if we go from the products back to the reactants. So like a roller coaster like Mr. Freeze, where it goes forward, and then we can also go reverse. So reactions can go forward and reverse, many of them, okay? So when we say reverse, we mean starting with the products going backwards. It's not going to change the actual diagram, but that's what we're looking at. Okay, so what did we already learn also is that between the reactants and products, that is the delta H. In this case, because the reactants are higher in energy, that means that this number is negative, okay? And that makes that losing energy, which is exothermic. The last little bit of information to put in here is, that must be the activation energy, and indeed it is. The activation energy needed to react. So it's like getting up the hill of energy to get to the reaction. So it's like a roller coaster, like I said. It's got to get up, then it can roll along the reaction. So between the reactants and the top of the hill of the reaction profile is, whoops, I'm sorry, I didn't mean to write that. Yikes, I hate when it's messy. It is activation energy. It's not a change in, it's just the energy needed. And if we do not have that energy, we do not get to react. So if you're going to buy something at a store, you have $80. If you're going to do this legally, you have to have $80 plus tax, whatever, right, to legally get them, or you leave without the shoes. Okay? So pause the video for just a sec and come back and fill the other diagram in. It's the same idea. All right, so hopefully you paused this and already filled this in. Again, from reactants up to the top of the hill, that's our activation energy. Reactants, between the reactants and products is our delta H. In this case, we're going higher, so that's a positive value, and that would make this endothermic. So you hopefully are saying how kind of simple they are. So you're going to check. Here's what we're going to be doing for our ideas here. We're going to do speedy check 1 through 3 and 18. So try those and bring those to class tomorrow. That is in your other packet, marked Speedy Check with Speedy Gonzalez on the front. We're going to refer to that throughout this entire packet. Factors that affect reaction rates. I know we have to go a little further, so let's talk about what affects how fast something reacts. So first of all, it's just what they are, nature of the reactants. Like it just depends on ionic, London dispersion, bond strength, structure, how it's put together, if we're going to use a catalyst or not, which we're going to talk about in a little bit. Concentration, so how concentrated is it? Do we have a lot of it or do we have less of it? We'll talk about that, and that relates to pressure. Temperature, how high or low that temperature is. We'll talk about how that is affected, and surface area. So is it just small little pieces? Is there more in the surface, or is it like I have to take how many licks to get to the center of a lollipop? So we'll talk about that. Okay, so concentration, we're going to take that one first. Concentration is defined as the number of molecules per unit volume. So how much is there? So you can see I've drawn a lower concentration. I have less molecules in this area. Okay, now I'm obviously not going to draw them exactly the same, but you're visualizing if these were the same area. Okay, even though I know they aren't because I just hand sketched them, they would have less molecules here than here. It's just like the halls, guys. You know, when there's more students in the hall, you're going to bump into more people and you're going to go slower, right? But in this case, that's not how it happens, okay? You're going to bump into more people, but when you bump in, it causes actually the collisions make the things go faster. So the higher the concentration, the faster the reaction rate. So they're going to run around and be like, okay. So faster you are going to go. The lower the concentration, there isn't as much to bump into. They're kind of less energy-ish usually. And that means less collisions, you're going to move slower. Okay, so again, lower concentration, they're not as much to react. They're going to be slower. But if you have a lot of things reacting, they're going to be like, woo, 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 let's go faster. All right, so that's concentration. Temperature is what you think also, because again, at higher temperatures, we have higher speed because it's the average kinetic energy that creates more collisions, faster reaction rates. So as the temperature increases, we get faster reactions. That should make sense. And as the temperature drops, that means we're literally chilling out. We're moving slower, as it says here. We have less energy, the collisions get less, and the reaction is slower. That is why we have refrigeration. Refrigerating food and things like that causes the decomposition of that food to occur slower. So it slows down that reaction rate. Pretty nifty, right? All right, so you have a little summary there. Last thing we're just going to talk about in this little area is catalyst. Oh, you know what? I don't know. Where did that go? You know what? I'm not sure why that's not in the notes. Hold on just 2 seconds before I forget, or I'll explain it. Oh, it is on the back side. Okay, I'm going to come back to catalyst. So I just want to make sure we have the other factor. So surface area is another factor that affects reaction rates. We're going to stop right here today. You're going to also go through 12 after this. Okay, so speedy check all the way up to number 12. Surface area, the smaller the particle size, meaning like if you have granulated sugar, okay, compared to a sugar cube, takes me just a sec to draw, sorry. And we have a cube, ooh, that's been eaten by the horse already, sorry. A sugar cube with less surface area, right? Why? Because there's less on the surface. There's a lot down in the bottom, like I was saying about the lollipop, right? So it has less surface available right at this point. Now, if you grind it up, of course, yeah, this one has more surface because they're all little bitty particles. And how's that going to affect it? Of course, the more surface, say you're dissolving it, that water's going to go, whoop, okay, I'm done. So the reaction is going to go much faster if you cut it up. So this is like having your potatoes. When you boil potatoes, you don't put the whole potato in there. It's going to take forever because there's not as much surface area. So if you cut it up into smaller cubes, and the smaller you make them, technically, the faster it will cook. So, of course, if you have more surface area like that entire potato, it's going to take a lot slower. So these are pretty logical, right? I'm hoping you're seeing how logical they are in the real life examples. Last thing to mention is the catalyst. We'll do this really fast. Ooh, haha, speedy, speedy. Because that's what a catalyst does. It speeds up a reaction, all right? Now, I was talking about those shoes earlier where we had to get to this price, right? This activated, and I'm going to give you another term. We call this very peak an activated complex, okay? I know that sounds fancy. It just means, hey, how much energy? So this could say, I need 100 joules, okay? So like our shoes, we would need $100 to get those shoes plus tax. We're just going to ignore that for now, right? But $100 with tax, all right? And then a catalyst is going to take a new pathway. So a catalyst has a new pathway, okay? And I know I shouldn't have drawn it there because they both end up in the same spot. It's not changing the reaction without changing the reaction. So it's actually not part of the reaction itself. It's just something that goes along and says, hey, move faster. Let's go. Kind of like me saying, go, go, go. Get this done. And so now my activated complex here is lowered, and I don't really have a shortcut to writing this out, is lower the amount of energy. Okay, energy is another word, obviously, but that's the activation energy total. The activation energy would be the difference, right, from here to here. So you're really talking about the complex being at the top. So this activation energy here, look at the difference in that activation energy, right? This is activation energy without a catalyst. This is EA with a catalyst. And so what happens, we have a sale on those shoes. So catalysts are like sales. You're like, okay, whoop, whoop, whoop. Well, now instead it's going to be 60 joules of energy. So you can get there much faster. You don't have to go as high on a hill with these reactants. You don't have to get as much energy. That's a much smaller amount than that, right? It's almost actually less than half, okay? So it is like now, okay, you can walk in and you can get those shoes for $60 for, leaving, okay? So that is what a catalyst does. It speeds up everything. We have many catalysts in our world. One of the most important types are enzymes. You've heard of them in PhysPath and hopefully biology and things like that. They are a ton of them. There are a ton of them in our bodies. They speed up complicated reactions. Things that like, oh, let's regulate our temperature. That's not easy, guys. Our bodies are amazing. Let's keep our blood between a certain pH, very, very narrow pH. I gave you an example of carbonic anhydrase. They always have kind of funky names, some of them. Enzymes that speed up the reaction between carbon dioxide and water to help prevent excess carbon dioxide in the blood, okay? So that's a big thing because we can die from that, of course, right? Ozone, of course, is catalyzed by our chlorofluorocarbons. You've seen the CFC idea where they've destroyed supposedly the ozone. Well, that's what they are doing. O3 is being broke down into O2, which is just oxygen in the air, and it's not necessarily a bad thing. Sometimes you can get more bad things, but the chlorine especially involved in these, there's fluorine and chlorine and stuff like that, and that's usually in aerosols and stuff like that, like cans that spray like hairspray. That's why you don't find a whole lot of those anymore in a different kind of form. So, all right, finish speedy check 1 through 13, and I'll see you tomorrow.